Hello friends, continuing with the topic of electrical capacitance. Today we come to ninth part of this topic, common potential across parallel combination of two capacitors C1 and C2 charged to different potentials V1 and V2 respectively, and energy stored in the combination. I repeat, common potential across parallel combination of two capacitors C1 and C2 charged to different potentials V1 and V2 respectively, and energy stored in the combination. Let us start with, first we develop physical situation. Consider two capacitors C1 and C2 charged to different potentials V1 and V2 respectively. Then charge stored in each capacitor will be, say, Q1 equal to C1 V1 and Q2 is equal to C2 V2 respectively. Energy stored in the capacitors will be U1 equal to half C1 V1 square and U2 equal to half C2 V2 square respectively. The total energy stored in both the capacitors before combination, say U0 is equal to U1 plus U2, and it is equal to half C1 V1 square plus half C2 V2 square. Now second step, common potential across combination. Total charge in combination of capacitor be, say, Q is equal to Q1 plus Q2. Now the two capacitors are connected in parallel as shown in diagram. The charge sharing will take place till combination acquires a common potential, say V dash, as shown. Then V dash is equal to Q divided by C dash, or it is equal to Q1 plus Q2 by C1 plus C2, or it is equal to C1 V1 plus C2 V2 divided by C1 plus C2, where C dash is equal to C1 plus C2, because when two capacitors are connected in parallel, their equivalent capacity is equal to algebraic sum of the two capacities. Okay. Or V dash is equal to C1 V1 plus C2 V2 divided by C1 plus C2, and is the common potential across the combination. Now second, energy stored in the combination. Say U dash is equal to half C dash V dash square, and is equal to half C1 plus C2 for C dash, and C1 V1 plus C2 V2 divided by C1 plus C2 for V dash. So U dash is equal to half C1 plus C2 into C1 V1 plus C2 V2 divided by C1 plus C2 whole square, or finally we say U dash is equal to half C1 plus C2 into C1 V1 plus C2 V2 divided by C1 plus C2 whole square. So this is how we have the common potential across combination and energy stored in the combination. when the two capacitors are connected across each other or they are connected in parallel. Now, because U dash is less than U naught, therefore the difference U naught minus U dash is lost as power dissipation during sharing of charge in the connecting wires. That is, this energy is dissipated in the form of heat radiation due to resistance of connecting wires. Assignment 2.3, question number 17. A capacitor C0 is charged to potential V0 from a battery and disconnected. Then connected across an uncharged capacitor C dash. A. Calculate common potential difference across the combination. B. Calculate energy stored in the combination. C. How does this energy change? D. Where does the difference in energy go? So these are 4 questions you have to answer in this situation. Now solution to question number 17. First, we develop physical situation. Consider 2 capacitors C0 having charge Q and PD as V0 as shown. Then charge stored in capacitor will be say Q equal to C0 V0. Energy stored in the capacitor will be say U0 equal to half C0 V0 square. Now, an uncharged capacitor C dash is connected across C0 as shown in diagram. The total capacity of the combination will be say C equal to C0 plus C dash. Let us mark it as equation 1. 2. Common potential difference across combination. The charge sharing will take place when an uncharged capacitor C dash is connected across a charged capacitor C0 till the combination acquires a common potential say V dash as shown, such that V dash is equal to Q by C0 plus C dash. Let us mark it as equation 2. 3. Energy stored in combination say U dash is equal to half C into V dash square, and it is equal to half C0 plus C dash into Q divided by C0 plus C dash square, because C is equal to C0 plus C dash and V dash is equal to Q by C0 plus C dash. And finally, on simplification we get U dash is equal to half Q square by C0 plus C dash, or U dash is equal to C0 divided by C0 plus C dash into Q square by 2 C0, or it is equal to C0 divided by C0 plus C dash into U0, because U0 is equal to half Q square by 2 C0. Or finally we get U dash is equal to C0 divided by C0 plus C dash into U0. Now U dash is less than U0, and the difference U0 minus U dash is dissipated as heat due to resistance of connecting wires during sharing of charge. So when C0 is equal to C dash, half of the energy is lost during sharing, because in that case U dash will be equal to half U0. Assignment 2.3 continued. Question number 18. A 5 microfarad capacitor is charged by a 100 volt supply. The supply is then disconnected and the charged capacitor is connected to another uncharged 3 microfarad capacitor. How much energy of the first capacitor is lost in the process of attaining steady situation? Question number 19. A 600 picofarad capacitor is charged by 200 volt supply. It is then disconnected from the supply and is connected to another uncharged 600 picofarad capacitor. How much electrostatic energy is lost in the process? And here we finish with the topic of electrical capacitance. Next time we will start with fourth part of this chapter, Van de Graaff high voltage generator and particle accelerator. Thank you so much. Goodbye till then.